In 1994, a mathematician at Bell Laboratories named Peter Shor published a paper that sent a quiet but unmistakable tremor through the worlds of mathematics, computer science, and national security. The paper described an algorithm, a set of mathematical instructions for solving a specific problem, that if run on a sufficiently powerful quantum computer, could crack the encryption, protecting virtually every secure digital communication on Earth. Bank transactions, government communications, private messages, medical records, the infrastructure of the entire modern internet. All of it rested, and still rests today, on a mathematical problem that Shor's algorithm could theoretically solve with terrifying efficiency. The National Security Agency took notice. Cryptographers around the world took notice. And 30 years later, Shor's algorithm remains one of the most consequential and carefully watched results in the history of computer science. Today, we are going to understand exactly what it is, how it works at a conceptual level, why it matters so deeply, and, crucially, where things actually stand right now in terms of the real-world threat it poses. To understand why Shor's algorithm is so significant, you first need to understand the mathematical foundation of modern encryption. The most widely used public key cryptographic system in the world is called RSA, named after its inventors Ron Rivest, Adi Shamir, and Leonard Adleman, who published it in 1977. RSA encryption is built on a deceptively simple mathematical observation. Multiplying two large prime numbers together is easy, but given the result of that multiplication, working backward to find the original two prime numbers is extraordinarily hard. If I give you two large primes, say each several hundred digits long, you can multiply them together in a fraction of a second. But if I give you only the product and ask you to find the two factors, the best classical algorithms known would take longer than the current age of the universe to find the answer for numbers of the size used in modern RSA encryption. This asymmetry, easy one way, impossibly hard the other, is the mathematical trapdoor on which RSA security is built. It is not proven to be hard in an absolute mathematical sense. There is no proof that no efficient, classical algorithm for factoring exists. But after decades of the world's best mathematicians trying to find one, none has been found, and RSA has remained secure in practice. Shor's algorithm changes this picture completely, at least in principle. What Shor showed is that a quantum computer can factor large numbers exponentially faster than any known classical algorithm. The key word is exponentially. This is not a modest improvement. For a number with n digits, the best classical factoring algorithms take time that grows roughly as an exponential function of the cube root of n. Superpolynomial time. In mathematical language, Shor's algorithm runs in polynomial time, meaning the time it takes grows as a manageable power of n rather than an exponential. For the key sizes used in real-world RSA encryption today, typically 2,000 to 4,000 bits. This difference translates from computations that would take classical computers billions of years into computations that a powerful enough quantum computer could theoretically perform in hours or less. How does Shor's algorithm actually achieve this? The deep answer involves quantum Fourier transforms and the mathematical structure of the factoring problem. But the conceptual heart of it is this. Shor realized that the problem of factoring a large number can be transformed into a different problem. The problem of finding the period of a particular mathematical function. Period finding is something that quantum computers can do extraordinarily efficiently using quantum Fourier transforms. which are quantum analogues of a classical mathematical tool called the fast Fourier transform. By using superposition to evaluate the function at many inputs simultaneously, and then using quantum interference to extract the period from that superposition, Shor's algorithm sidesteps the exponential difficulty that makes classical factoring so hard. It is a breathtakingly elegant piece of mathematics, and it represents a genuine, proven quantum speedup for a problem of enormous real-world importance. Shor's algorithm does not only threaten RSA, it also breaks elliptic curve cryptography, which is the other major family of public key cryptographic systems in widespread use today, and which underpins the security of Bitcoin, as we discussed in an earlier video. The discrete logarithm problem that elliptic curve cryptography relies on is also efficiently solvable by a variant of Shor's algorithm. This means that essentially all of today's public key cryptography, the layer of security that allows your browser to establish a secure connection with a website, that allows your bank to verify your identity, that allows governments to communicate securely, is in principle vulnerable to a large-scale quantum computer running Shor's algorithm. Now here is where honesty becomes essential, because this is exactly the point where the gap between theoretical result and practical reality is widest and most frequently misrepresented. Running Shor's algorithm against real-world RSA encryption requires a quantum computer of a scale that does not currently exist and will not exist for a very long time, if current engineering trajectories hold. Estimates from serious academic research suggest that breaking 2000-bit RSA encryption with Shor's algorithm would require on the order of 4,000 logical qubits running for a matter of hours. Logical qubits are error-corrected qubits, reliable qubits built from many noisy physical qubits through quantum error correction schemes. Given the error rates of current physical qubits, producing a single logical qubit might require anywhere from hundreds to thousands of physical qubits, depending on the hardware platform and error correction code used. Scaling that up to 4,000 logical qubits implies needing millions of physical qubits working together reliably. And the best quantum computers today have a few hundred to a few thousand noisy physical qubits with error rates that are still far too high for the error correction overhead required. The gap is not small, it is enormous, and closing it is the central engineering challenge of the quantum computing field. There is also a concept that has begun circulating in security circles called harvest now, decrypt later. The concern is this: even though a quantum computer capable of running Shor's algorithm at scale does not exist today, an adversary with sufficient resources and foresight could intercept and store encrypted communications today, archive them, and then decrypt them years or decades from now when the necessary quantum hardware becomes available. For data that needs to remain secret for a long time, classified government communications, medical records, long-term financial data. This represents a genuine present-day concern, even if the decryption capability itself is future. This is one of the reasons why the transition to post-quantum cryptography is not something that can wait until quantum computers are actually powerful enough to run Shor's algorithm. The response from the cryptographic community has been substantial and serious. NIST, the National Institute of Standards and Technology, ran a years-long public competition to evaluate and standardize post-quantum cryptographic algorithms, systems designed to be secure against both classical and quantum attacks. In 2024, NIST finalized its first set of post-quantum cryptographic standards based primarily on mathematical problems involving lattices, which are believed to be hard even for quantum computers. The migration toward these new standards is underway across government systems, technology companies, and internet infrastructure, though it will take years to complete given the scale of what needs to be updated. Peter Shor's 1994 paper is one of those rare results that simultaneously solved a profound theoretical problem and created an urgent, practical challenge that the world is still working to address 30 years later. The algorithm is real. The mathematical speed-up it provides is proven. The threat it poses to current cryptographic infrastructure is genuine. And the engineering challenge of actually building a quantum computer capable of running it against real-world encryption remains one of the greatest unsolved problems in technology. All of those things are true at the same time, and holding all of them in mind together, without collapsing the nuance into either dismissal or panic, is what it means to think clearly about one of the most consequential algorithms ever written.